6.5 billion kilometers from where you're sitting right now, there is a small, icy world with a heart carved into its surface, mountains made of frozen water, and an atmosphere that behaves like nothing else in the entire solar system. For decades, we thought we finally understood it. Then, the James Webb Space Telescope turned its mirrors toward it, looked in a kind of light no instrument had ever used on this world before, and found something that made scientists go back and question a hypothesis nobody had been able to prove for almost a decade. This is the story of how Webb looked at Pluto, and why what it found shouldn't have been visible at all. To understand why this observation mattered so much, you have to go back to 2015, to the moment humanity actually got close enough to Pluto to see it properly for the first time. NASA's New Horizons spacecraft, after a 9-year journey across the solar system, flew past Pluto on July 14, 2015, and sent back images that reshaped everything scientists thought they knew about this small, distant world. Before that flyby, Pluto had been little more than a blurry smear of pixels, even in the best images Hubble could manage. New Horizons revealed a place of genuine, staggering complexity. Mountains made of water ice, rising kilometers into a nitrogen sky, a vast, heart-shaped plain of frozen nitrogen and carbon monoxide informally named Tombaugh Regio, dark, reddish terrain near the equator called Cthulhu Macula, and wrapped around the entire planet a thin, hazy atmosphere, layered and structured in a way nobody had predicted, dominated by nitrogen, methane, and carbon monoxide. That haze became one of the most persistent puzzles to come out of the entire New Horizons mission. Because when scientists looked closely at Pluto's atmosphere, the numbers didn't add up. Pluto sits so far from the sun that it receives only a tiny fraction of the sunlight Earth does, and yet its atmosphere behaves in ways that seem to require far more energy exchange than that faint sunlight could easily explain. In 2017, a planetary scientist at UC Santa Cruz named Xi Zhang proposed an explanation that, at the time, sounded almost too elegant to be true. He hypothesized that the haze particles filling Pluto's atmosphere weren't just passive decorative structures drifting in the wind. He proposed they were active participants in the atmosphere's energy balance, absorbing sunlight during the day and radiating that heat back out as infrared radiation, effectively acting as a kind of thermostat for the entire atmosphere. If true, it would make Pluto's atmosphere fundamentally different from every other atmosphere we had ever studied anywhere in the solar system, Earth included. The problem was, nobody could prove it. Confirming a hypothesis like that requires directly measuring infrared thermal emission coming from those haze particles, isolating a very specific kind of heat signature from a target so distant and so faint that, for years, no instrument available to astronomers was sensitive enough to detect it. New Horizons had given us close-up images. It had not given us that. The Hubble Space Telescope, extraordinary as it is, was not built to see in the wavelengths that would reveal this particular signature clearly. For nearly a decade, Zhang's idea sat there, plausible, elegant, and unconfirmed, waiting for an instrument that didn't yet exist. Then the James Webb Space Telescope launched, and years later, scientists finally had the tool this hypothesis had been waiting for. Here's where the story gets genuinely surprising, because Webb was never built with Pluto specifically in mind. Its headline mission is looking back toward the earliest galaxies in the universe, capturing infrared light that has been stretched and reddened by billions of years of cosmic expansion. Pluto is, cosmically speaking, sitting in our own backyard. But it turns out the same instrument sensitivity that lets Webb detect the faint infrared glow of galaxies billions of light years away also makes it extraordinarily good at detecting the faint infrared glow of a small, cold world just a few billion miles from home. A team led by Tanguy Bertrand at the Observatoire de Paris, working with an international group of researchers, including scientists from the CNRS, the University of Reims, and Xi Zhang himself at UC Santa Cruz, pointed Webb's MIRI instrument, the mid-infrared instrument, directly at the Pluto-Charon system. This was, in a very real sense, the first time Pluto had ever been studied in this specific slice of the light spectrum. Previous observations, from Hubble to New Horizons, had never had an instrument sensitive enough to capture Pluto's mid-infrared thermal emission with any real clarity. MIRI changed that. Working across observations taken in 2022 and 2023, the team used Webb to capture thermal light curves of both Pluto and Charon at 4 specific wavelengths, 15, 18, 21, and 25 microns, each one revealing subtly different information about how heat moves across the surface and atmosphere of these two worlds as they rotate. Then, in a follow-up observation in May of 2023, Webb captured something even more detailed, a high-resolution mid-infrared spectrum of Pluto, spanning nearly 5 to 27 microns, essentially a complete chemical and thermal fingerprint of the dwarf planet's atmosphere, rendered in a range of light no instrument had ever managed to resolve this clearly before. And when the team analyzed what came back, the pattern was unmistakable. The haze in Pluto's atmosphere really was doing exactly what Xi Zhang had proposed back in 2017. It was absorbing incoming energy and re-radiating it as heat in a way that measurably shaped the temperature structure of the entire atmosphere, confirming for the first time with direct observational evidence that Pluto's atmosphere runs on a completely different kind of energy balance than anything else we've ever studied in the solar system. Zhang himself described the moment with the kind of understated excitement only a scientist waiting nearly a decade for confirmation can really deliver, noting how rare it is in planetary science for a hypothesis to be confirmed this cleanly, and how fortunate the team felt to see it happen. That alone would have been a landmark result. But the data held something else, something that added a genuinely eerie new layer to what we understand about this distant system. Pluto isn't alone out there. It orbits its sun in a mutual gravitational dance with its largest moon, Charon, a relationship so close and so balanced that the two bodies actually orbit a shared point of gravity between them, rather than Charon simply circling Pluto the way our moon circles Earth. And the new Webb data revealed something happening between these two worlds that doesn't happen anywhere else we've observed in the solar system. Material is escaping from Pluto's thin atmosphere, drifting across the gap of space between the two bodies and settling directly onto Charon's polar regions. This isn't speculation. It's consistent with surface mapping that shows darker reddish material concentrated at Charon's poles, thought to result from methane molecules escaping Pluto's gravity, drifting to Charon, and undergoing chemical transformation once they land, becoming trapped in a completely different, colder environment with no atmosphere of its own to protect or process them. Sit with that for a second. One small world at the edge of our solar system is quite literally shedding pieces of its atmosphere onto its neighboring moon, staining it a different color in the process. It's a planetary relationship, unlike anything else astronomers have documented anywhere else among the worlds we've studied, and it took an infrared telescope built to observe the birth of galaxies to finally capture clear evidence of it happening. Charon itself, in contrast to Pluto, turned out to be strikingly simple in the new data. It has no meaningful atmosphere of its own, though scientists haven't ruled out some seasonal outgassing at a much smaller scale. Its surface is dominated by water ice mixed with ammonia-based compounds, and outside of those reddish polar caps built from Pluto's borrowed material, its terrain is comparatively uniform. The contrast between the two worlds, one an active, chemically rich, atmospherically dynamic body, the other a quiet, largely inert companion, made the data even more valuable because it gave researchers a clean baseline to compare against when trying to understand exactly what makes Pluto's atmosphere behave the way it does. Now, why does any of this matter beyond satisfying curiosity about a small, distant world most of us will never see up close? Because Pluto's atmosphere, strange as it is, offers scientists something surprisingly valuable, a working, observable example of a very early kind of atmospheric chemistry. Researchers have pointed out that studying the nitrogen and hydrocarbon-dominated chemistry happening in Pluto's hazy atmosphere could offer real insight into the conditions that existed on early Earth, long before oxygen built up in our own atmosphere, back when our planet's air was similarly dominated by nitrogen and simple hydrocarbon compounds. In other words, this distant, frozen world sitting at the edge of the Kuiper Belt may be quietly preserving a chemical snapshot of the kind of atmosphere that once existed on our own planet, billions of years before anything resembling life had evolved here. There's a reason the phrase "shouldn't be possible" keeps attaching itself to this story, and it isn't hyperbole. Pluto sits so far from the sun and receives so little direct sunlight, roughly 1,000 times less than Earth does, that by conventional expectations, its atmosphere should behave in a comparatively simple, sluggish way, with very little energy available to drive complex thermal behavior. Instead, Webb's data revealed an atmosphere actively regulating its own temperature through haze particle behavior, material physically transferring between two separate worlds across open space, and a level of chemical richness that, prior to these observations, existed only as an unconfirmed hypothesis sitting in a 9-year-old paper. None of that fits comfortably with the old, simpler picture of Pluto as a frozen, static, geologically dead rock at the edge of the solar system. The picture that's emerging instead is of a small world that is, in its own quiet way, remarkably active, chemically alive, and still capable of surprising the scientists who have spent their careers studying it. It's worth remembering just how recently Pluto's reputation shifted in the public imagination. In 2006, it was famously reclassified from a planet to a dwarf planet, a demotion that, for many people, effectively marked the end of Pluto's relevance in popular astronomy. But that reclassification never reflected a loss of scientific interest. If anything, the years since have revealed a world far more dynamic and far more scientifically important than its old status as the 9th planet ever suggested. The New Horizons flyby proved that. The confirmation of Xi Zhang's haze hypothesis, using an instrument built for an entirely different purpose, proves it again. And this likely isn't the final word. Researchers involved in the project have already discussed the value of follow-up Webb observations of Pluto over time, tracking how the haze, the atmosphere, and the seasonal redistribution of surface ices change as Pluto continues its extraordinarily long orbit, 248 years to complete a single trip around the Sun. Pluto is currently moving away from its closest approach to the Sun, which occurred back in 1989, meaning its atmosphere is expected to undergo real seasonal change over the coming decades, potentially thinning as it grows colder and farther from the Sun's already faint warmth. Continued observations with Webb could let scientists watch that seasonal transformation unfold in something close to real time, a kind of long-term weather monitoring for a world 6.5 billion kilometers away. What makes this whole story so compelling isn't just the specific discovery about haze particles and infrared light curves, technical as that sounds, it's what it represents. A telescope built to look back toward the dawn of the universe, toward galaxies so distant their light has been traveling for over 13 billion years, turned around, pointed at a small, icy world practically next door in cosmic terms, and resolved a mystery that had been sitting unanswered for the better part of a decade. It's a reminder that the tools we build for one purpose often end up teaching us things about entirely different corners of existence, and that even the objects closest to us, the ones we think we've already mapped and explained and filed away, are still capable of holding on to real secrets. Pluto was never just a frozen rock at the edge of the map. It has an atmosphere that runs on its own strange internal logic. It is quietly reshaping the surface of its own moon, one escaping molecule at a time. And it took a telescope designed to stare into the deep past of the universe to finally prove that this small, distant world has been more alive, more active, and more chemically strange than almost anyone expected.